Hello. We're going to do 4 more units on SGD, stochastic gradient descent, including this one. These units are perhaps the most mathematically challenging part of this course, but at the same time, even if the details are sort of mysterious, I find this particular mathematics to be really interesting and pleasing. So I find it to be a lot of fun. So what's the big picture? The big picture is that I've shown that in practice, when you're training a network and you run at a constant learning rate, your loss reaches some converged loss value. Then you drop your learning rate by a factor of 2 and the loss goes down. You drop it by a factor of 2, the loss goes down again. So this suggests that if you hold the learning rate constant, there's some kind of stationary distribution or converged place you land. It's not the optimal loss value, but it's a distribution that floats above the optimal loss value due to the stochastic variation of the stochastic gradient descent. And I've argued that if we think in terms of the temperature of that converged stationary distribution, we want to understand the hyperparameters in terms of what temperature corresponds to what setting of the hyperparameters, such that when you change the batch size or the momentum, you can keep your temperature schedule the same, because the temperature schedule seems really important. It seems like a fundamental issue in SGD. Now, I didn't define temperature. I didn't mathematically show that we have something that exactly corresponds to temperature. But I'm going to try to move in that direction. So I'm going to do mathematical analyses that really give us a picture, a mathematical picture of temperature and what this stationary distribution looks like. But this mathematical analysis is going to be a little bit strange. It's going to move to continuous time differential equations, and it's going to move to smooth continuous densities over parameter space. And that is what's going to make this a little bit challenging. We have to make this movement from discrete updates of the parameter space, each update of SGD, to thinking of that as continuous in time. And the easiest transition to continuous time is something called gradient flow. So I'm going to do that first. The first thing we're going to do is gradient flow. So we have a total gradient, right? The total gradient is defined to be the average over our training set of the gradient of the loss, or the gradient of the average loss. And this total gradient is not stochastic, right? It's a precisely well-defined thing for any given parameter vector. It's the average over all the training data of the loss. So we can define a differential equation that says the time derivative, and I'll talk about what time means in a moment, but I'm just going to define the time derivative of the parameter vector to be minus the gradient. So we're going to go down the gradient deterministically according to a differential equation, according to this differential equation. And that is gradient flow. Right now we've got a deterministic path differential equation we're going down. Now this differential equation can be numerically approximated, right? I can take finite steps and approximate this differential equation. So I'm going to take the change in the parameter vectors to be the derivative we want times delta t for some finite delta t, just numerical simulation of this. Now, I'm going to interpret this delta t as the sum of the learning rates over some number of learning rates. So let's think about that. If I'm running at a small learning rate, right, so that the updates at each step are not changing the parameter value much, then if I take a large number of steps and ask, what's the expected change, the average change in the parameter vector over a large number of steps? Well, that average change is just the average gradient, the expected gradient, summed up times the learning rate over that sum. So the expected delta phi in a finite step SGD is minus the gradient times the sum of the learning rates along the way, right? So I can interpret this numerical integration of this as saying delta t corresponds to a sum of learning rates. So I can take any discrete thing, any discrete SGD with learning rates, just interpret the sum of the learning rates as time. So I've already said this. We can interpret delta, this slide says we can interpret delta t as the sum of the learning rates, and interpret the sum of the learning rates as a kind of time. Okay, so there are different limits we can take. So I'm particularly interested in a limit. If I wanted to, in a limit where we consider a bunch of updates, right? Our updates are going to be of this form. So we've got how many updates we can take. That's capital N. And we're going to take the learning rate to 0. What we're going to define is a limit of SGD that corresponds to this differential equation, gradient flow. We're going to take the learning rate to 0, but we're going to take the number of steps to infinity. And we're going to do that such that the sum of the learning rates is t. So we do that by setting t equals n times the learning rate, or n equals t over the learning rate. Okay, so I'm holding t fixed, but I'm taking the learning rate to 0 and the number of steps to infinity as we hold t fixed. And what we want to convince ourselves of is that limit really does correspond to the differential equation. That in that limit, what's going to happen is that the parameter value that we end at, which is the parameter value at time t, is the result of integrating that differential equation to time t. And we can do that intuitively. In this class, there's going to be lots of intuitive physics style arguments. We can do that intuitively by taking this long sequence and dividing it into the square root of n blocks, each of length the square root of n. So what's happening is the time within each block, the sum of the learning rates within each block is going to 0, right? Because the total time is fixed at t. So the time within each block is going to 0, but the number of updates within each block is going to infinity. So we've got something that's essentially taking 0 time, but using an infinite number of updates. So within this one block, we're going to get something that converges to an exact estimate of the average gradient, because we've got a number of updates that's going to infinity. But the time is going to 0. So we're getting a very small delta t here, where the gradient estimate is very accurate. And that's happening within each block. So this is essentially integrating the actual differential equation. So this is a kind of proof that this particular limit does correspond to the gradient flow differential equation. Okay, so that's the end of this unit. This unit's very short. It's just the first transition to continuous time, which is the gradient flow. Thank you.